today. Okay, you're recording. So you're recording. Let's see. All right, guys. So last time we looked at the development of the microstructure in the binary eutectic system in the same way we did in the binary isomorphous system, or phase diagram if you want. And we have seen how the microstructure develops for the different cases. Here in this case we said it's different than the binary isomorphous, that you will develop different microstructures at different compositions from 0 to 2. We looked at that, from 2 to 18, and we looked at specifically at the eutectic microstructure. What would that be? And we have seen that. It is this lamellar configuration. And we also looked at the development between 18.3 nearly to 61.9, how the microstructure develops. In this case, we said as you cool down, there is a primary or pro-eutectic microstructure, pro-eutectic alpha, which develops beforehand, and then up to a maximum, which it reaches just before the eutectic isotherm here. And then once you cool down, what happens in the cooling down just below the eutectic isotherm, that let's say that this alpha primary phase remains, because it's already transformation is done there, it's a solid, so this remains. What is going to transform is the liquid to this lamellar configuration in the same case, the same way, and the same reason for why the eutectic isotherm, which we have explained here last time, why it develops. It needs to do that fast, and it needs to form two phases, alpha and beta, which are actually considerably different in terms of the composition. One is at 18.3% by weight 10, and beta is at 97.8% by weight 10. So that was the development of the microstructure. Now let us see the issue, the problem of if you remember, we in the last lecture maybe we did this. We said we practice just to determine if we are at a certain temperature and a composition. We practice here what are the phases which will be there, and what are the compositions and proportions as well. Let us do it now correctly, in the correct way. In order to determine that, we need also to know the history of heat treatment. Where was it heat treated from? Was it from here, there? As you can see, at different compositions, we are getting different microstructures. Now, in this case that we are having here, let's see what we are going to have as we cool down to just below this. So if we are at this point, if we are given, like, you cool down, if the material, as the alloy was cooled down from, let's say, above 330 degrees centigrade, slowly up to until it reaches just below the eutectic isotherm, or below that, or a certain temperature is given as well. We will have the same case, but let's take the easy one, just below the eutectic isotherm. What will the microstructure, how the microstructure will develop? Now, if I tell you that, if I ask you that, if we cool down from here to there, what microstructure we are going to get? Well, it's not only alpha and beta, and you know that. It is the alpha primary, which we already said, that's the primary alpha. And then we have also the lamellar configuration, which formed, the liquid formed into this lamellar configuration, which you have here, which is the eutectic alpha and the eutectic beta. So these are the three different phases. This is a circular microstructure. These are lamellar configurations, as you could see them. Now, so if I tell you how many phases will be there, you will say alpha, beta, and alpha prime as well, as we are mentioning here. So these are the three phases, let's say, and what they are. This is the answer for what they are. What is the composition of the alpha, beta, and alpha prime? Of course, the alpha prime will have the same composition as the alpha. So in order to find their compositions there, add just below the eutectic isotherm, you draw a tie line. Where is that tie line? It is this tie line, right? So the composition of you intersect with the alpha phase here, and you draw a vertical from there. You will get nearly 18.3% by weight 10. And for the for the composition of the beta, beta is here. So the tie line is intersecting that. You drop a vertical from there. The composition of the beta which you have is 97.8. So what will be? So that's the composition. Now we want to know the proportions. What is the proportion of the alpha, of the beta, and of the alpha prime? Of course, we want to know. And this, I don't want to draw this here so that you don't get confused. That here we have an extra phase which formed and in this area, in this triangle actually. So what are the proportions which we have in this microstructure? In order to find the proportions there, we need to first of all find the proportion of the alpha prime, because it forms above the eutectic isotherm. So it's easy when they are only two parts to find the only two parts, that we have a liquid and we have the alpha. So it's easier here to find their proportions here. So we can go just above the eutectic isotherm and find how much alpha you have and how much liquid you have. That's the microstructure we are looking at. If we know how much alpha and liquid we have, then we know how this alpha just above the eutectic isotherm, which will be the alpha prime which we are having here. This is the proportion of the alpha prime, and it's not going to change. From here, how do I know the proportion of the alpha and liquid? Again, I draw a tie line as it is drawn here. The tie line intersects the alpha phase at this point, and it intersects the liquid. This is liquid zone here at this point. And from there, you can drop a vertical here, and from here you drop a vertical. Again, the composition of the alpha is 18.3, which is shown there again, and the composition of the liquid will be 61.9, nearly that much, which is written here, which is the eutectic composition basically, because we are just above the point for the isotherm. So this is the composition of the liquid, and that's the composition of the solid. Now, in order to get the weight fraction of alpha is equal to, or the weight percentage, it will be what? Using the Lever's rule. It will be S, that segment of the tie line, divided by S plus R, all that. So this is what we are saying. It's S divided by S plus R. That's the weight fraction of W alpha, the weight fraction of alpha. And that is how much? S is equal to how much? S is equal to 61.9, which is the segment, 61.9 minus 40. So that is this length here. From here to there, it is equal to 61.9 minus 40. So this is what we will have here. Move just now. This again. So this will be 61.9 minus 40. Okay, and divided by R plus S, which is the total, which is this S plus R there. So we are having all that S plus R, and S plus R will be all this from here to there. So instead of getting S alone and R alone, we can just say it is 61.9, which is from here, minus 18.3, which will give you the S plus R complete. So this will be 61.9 minus how much? 18.3. 18.3, and of course that fraction is multiplied also everything by 100. So you will get, if you work out this 61.9 minus 40 divided by 61.9 minus 18.3 and multiply by 100, you will get the result 50%. So this means that the amount of the alpha here is 50%, and the liquid of course will be 50% because you have two phases here. If the alpha is 50%, then the liquid again it's 50%. So the weight fraction of the liquid is equal to 1 minus alpha or weight fraction of alpha times 100. That gives you also 50%. Of course, you notice something. You are specifically at that position, you are getting 50% alpha and 50% liquid. If you were coming from here to there, let's say at another composition, and you were cooling up just above that, the percentages will be different, because now here at this point it will be the weight fraction of alpha will be this proportion divided by the total. Of course, the alpha will be much more, right? So in this case, it was a coincidence that we have 50% liquid and 50% alpha solid solution. Now, once we got the alpha and we said we got the alpha prime, and now we know that the alpha prime is 50%. If we go down just below the eutectic isotherm, what is going to happen? That alpha, which we have here, remains the same alpha, which is here, which is the alpha prime. It remains, it does not change. Let's call it alpha prime. That alpha prime remains as it is because it is already transformed to the solid. What is going to change is this liquid. We have no liquid below the eutectic isotherm. No liquid could stay. So all that liquid is going to change fast into this lamellar configuration, which is the alpha plus beta alternating layers. So alternating layers of alpha beta is going to form there. So where this lamellar configuration formed from? It formed from the liquid here. How much was the liquid? It was 50%. So all this lamellar configuration is all together is 50% of the microstructure, and the other 50% is this alpha prime. So alpha prime is 50%, and the lamellar configuration which you have here is the other 50% there. Now, if we want to find for this lamellar configuration how much proportion you have in terms of alpha or how much in terms of beta, we do the same thing to just below the eutectic isotherm. So we draw again a tie line which we have here. It intersects the beta here and it intersects the alpha here. And now we find, let's say, weight fraction of alpha is equal to the far segment, which is S, divided by S plus R. And this is what we are doing. So the weight fraction, the composition, which we already looked at that, it's 18.3. And the composition of beta is equal to 97.8. Weight fraction of the weight fraction, I need to write something here. Weight fraction of alpha is equal to the S, all that S, because it's the far segment from the alpha phase here. It's equal to the S divided by all that S plus R. And S is equal to, in this case, how much? It's 97.8 minus 40. So this is what the S is. It's 97.8 minus 40. And the S plus R, which we have here, it's all that segment from there to there. And that is equal to how much from here to there. Of course, I need to draw a horizontal line instead. It's 97.8 minus 18.3. So you can write it there. So it's 97 0.8 عدل yes minus 18.3. Of course, that fraction is multiplied by 100 and you will get 73%. If you want, this is the weight fraction of alpha. If you want the weight fraction of beta, you can just say 100 minus 73%, since you are talking about two phases here. 100 minus 73, so you can say 100 minus 73. You will get the beta that you have here. But assuming that calculation that we made, we are assuming that we are having 100% material, which is consisting of alpha and beta, the eutectic isotherm, the eutectic microstructure. But basically, this is basically 50% of the microstructure. It's not 100% of the microstructure, because 50% is alpha prime, and the other 50% is the alpha plus beta, which we have here, the lamellar configuration. And that's why if we want to get from the overall, actually, what we do here, we multiply this by 0.5, and we multiply this also by 0.5. Why we are multiplying by 0.5? Or you can say times 50 over 100, because it's basically 50% of the microstructure of the material, because this lamellar configuration formed from the 50% liquid. So you need, it is forming from only 50% of the microstructure, so it cannot be more. So this is 50% only, so that's why we multiply by 0.5 and 0.5 here. If you do that, let's do the calculation here, just to bring my calculator, my old calculator, 73. If you do calculate, if you multiply by 0.5, your result will be here 36.5. That's the correct answer for the alpha. This is the correct answer for the weight percentage of alpha from the overall, which you have here, and this results in also, which is 27 times 0.5, which gives you 13.5, okay, which gives you 13.5%. So what is that? That these are all percentages, okay? This is percent. So there. Now you could see from in the microstructure here that we have 50% alpha prime, 36.5% alpha, the blue one here, the lamellar configuration, and 13.5 the beta phase, the eutectic microstructure that we have here, the beta phase which we have here. Now if you add 50 plus 36.5 plus 13.5, it will add to 100%. This is how we should calculate it, and this is the amount or the proportion of the different phases that we are having here. Any question? Any questions, guys?
دكتور
Yes.
انت ضربت في النص عشان تطلع الالفا برايم ولا؟
انا ضربت في النص لان انا في هاي الكالكوليشن just below the eutectic isotherm, just below that، صح؟ الكالكوليشن اللي قاعدين نسويه هني لما نسوي when we use the Lever's rule is based on how much of the microstructure. It is based on that we are having 50%. This calculation for the alpha plus beta, which we have here, this alpha plus beta, this and that, these, is based on that we have only 50% of the microstructure. ولا لا؟ لأن it is, this lamellar configuration is formed from the liquid, and the liquid here is only 50%. The other 50%, which is the alpha prime, it remains as it is. You can see that, صح? So when you are doing the calculation for the alpha and beta here, they constitute 50% of the microstructure only, not more. So that's why we multiply by 0.5. إذا كان طلع لي هني إن liquid was, let's say, 40%, suppose it was 40%, here in the just above the eutectic isotherm that we had 40% liquid and 60% of course alpha prime, then what I would have done here is different. That we have only, if we are doing this calculation, we are going to multiply by 40 divided by 100. Yani we multiply by 0.4, and we multiply that also by 0.4 because it constitutes only 40% of the microstructure. So when you do the calculation, you are assuming you're having two phases here. When we did this, we are assuming we are having two phases here. No, it's not two actually. The third one is there, but we are in calculation. This which we did is out of 50% only of the microstructure. This is why we need to multiply that. Clear?
Clear.
Any other question? Okay, if this is clear, next we are going to just look at what we have done before. This is what in the development of the microstructure, we have three important microstructures in the binary eutectic phase diagrams there. If we are cooling, if we are at a composition which is the eutectic composition 61.9 nearly, if we are cooling at that composition down, we are passing through the eutectic point, we will get basically the eutectic microstructure, which is the lamellar configuration. All the material, all the microstructure will constitute of the lamellar configuration which you have here, as it is shown here. If we are below the eutectic composition, okay, and we refer to that as the hypo. Hypo means less. Hypo means less. Like when you say hypotension or hypertension. Hypertension يعني ضغط عالي مثلا، ضغط الدم العالي مثلا. Hypertension or hypotension, which means that less. So hypo basically means less and hyper means more. Hyperactive يعني activity ماله وايد. Okay, so this is what it means. So whatever microstructure is formed for composition less than the eutectic isotherm, than the eutectic composition, we call that hypoeutectic. And in the hypoeutectic, of course, we have the eutectic isotherm. As we are cooling it down there, we have the alpha prime, which is developing there. We have the alpha prime there, here, which are more or less a circular microstructure. And once we go below that eutectic isotherm, the lamellar configuration forms here. We call it also eutectic microstructure. So we have this hypoeutectic microstructure forming here. If we were above the eutectic composition, then we have very similar to that, but instead we are having the beta phase here. As you cool down, once you reach to the liquidus point or liquidus line there, the beta form, the beta prime, the primary beta is going to form, and then it increases in size until just before the eutectic isotherm will be the maximum amount of beta, which is beta prime, which is going to form. And if you drop just below the eutectic isotherm, the liquid, all the liquid, the remaining liquid is going to transform into the lamellar configuration of alpha and beta, which we have here. Very similar case to the previous one, but in this case, the primary beta has formed instead of the primary alpha, and this is called the hypereutectic microstructure there. So we basically divide the development of the microstructure into these main compositions with different compositions. In the binary eutectic phase diagrams, you will be developing different ones.
دكتور؟
Yes.
في اليوتكتيك نفسها يعني just below the eutectic point الكونفيجريشن اللي عندنا اللعبه configuration تكون بس اللايرز مال.
You mean at the eutectic صح؟
اي
at the eutectic composition. Yes.
اللاميلر configuration تكون بس اللايرز مال الالفا والبيتا صح؟
Yes. You can see that no? هاي اللي شرحناه الحصه اللي فاتت. This is what we explained last time. At exactly the eutectic isotherm, you will not have the primary alpha, nor you are going to have the primary beta. It's going, it's the solidification or melting is occurring across a point. And that's why you don't have development of any alpha prime or beta prime. It directly goes from the liquid to the lamellar configuration of alpha and beta. Okay?
Okay.
Now, let us look at the last and the most important phase diagram. This is the iron-carbon phase diagram, also referred to as the iron carbide phase diagram also. This is this phase diagram is the most, as I said, is the most important phase diagram because basically the ferrous alloys are the most important materials on the globe because we use them in the, it is the overwhelming material which is used actually. It is the most of the material which we use to make to do our things are the ferrous materials there, and specifically let's be in the it is the steels. Let's refer to that. This is the phase diagram. Let us introduce ourselves to the phase diagram. It looks a bit different, but it is the same phase the shape. So that's the temperature in degrees centigrade, and that's the composition. And the composition here is the composition of the carbon, which is shown here. The numbers which are shown there is the composition of the carbon. Of course, here you have 0 carbon. That means that you have 100% iron. And as you go in this direction, the percentage of the carbon is increasing and the percentage of the iron is decreasing. Now, if you notice here, unlike the other phase diagrams here, we went from 0 to 100%, for example, in the lead tin diagram or the copper nickel diagram or whatever. We went from 0 to 100. In this case, we are going up to 6.7% carbon only. Why? Well, basically because we are concerned with, first of all, we are concerned with the ferrous alloys, the steels here. We're not concerned with higher carbon content. And the cast irons forms actually at nearly 4 to 4.5% carbon only. So this is the maximum amount of carbon that we normally add. More than that, if we go to high carbon contents, let's say 80% or 90%, this is more or less graphite and it's not a steel anymore. So we are not concerned with the graphite. Of course, anybody wants to study the phase diagram of graphite, we will, if we are doing that, then we will be using that also. But basically for the studying of the iron carbon phase diagram, we don't need to extend for more than 6.7% carbon. Most of our work actually and the concentration is on this part actually, and less than 1% by weight carbon. So we don't need, but because we want to include the cast iron also here, so we go up to 6.7% by weight carbon. Now somebody can ask also, but you said 4.5 for cast iron. Why don't we stop there at 5? Why specifically this decimal 6.7% carbon? We are going to look at that in a minute. Why 6.7 also? Why not 5? Why not 4.5 where we don't need more than that for the cast iron to see the cast iron? 6.7. Well, we need 6.7 because basically here we have one of the phases which is the iron carbide, which is Fe3C. This here is not a phase basically. This is a compound. And there is somewhere I'm saying a compound Fe3C you have there also. This is basically a compound. What's the difference between a compound and a phase? Well, let's look at this phase, for example, alpha. The gamma. The gamma is called austenite. The gamma is a phase, and this phase can exist at different compositions. You see, if you go from this composition to this, to this, to this, to this, to this, this phase can exist. It can have different compositions there, up to there. بعدين something else is going to form, صح? This is the behavior of phases. Unlike the compounds only form at specific amounts of the constituents. يعني شنو مثلا? Let me make the life easy for you. Let's say H2O. H2O is a compound or a molecule if you want. It's a compound, right? Now, it forms specifically at a specific amount of hydrogen. You have 2 hydrogens and 1 oxygen. So you have an oxygen and you have a hydrogen here and a hydrogen here. It forms specifically at that fraction only. It does not form at any fraction. The compound has this stereotype behavior that it forms at that much only. The same thing for the iron carbide, which we refer to as the cementite. It forms only at 6.7% carbon. It does not form at any other compositions of carbon. And that's why, because we need also the cementite here, because cementite is important for our phase diagram, so we stop at 6.7 where the cementite forms there. So this is why we extend to 6.7% carbon. Now, let us acquaint ourselves more with the phase diagram. We have in the phase diagram there single phase regions. This is a liquid. Above this is the liquidus line actually. That is also the liquidus line. Above that everything is liquid. This is a single phase liquid which we have here. We have a single phase here as well. This is called delta ferrite. This is also called ferrite, but it's another type of ferrite. It's called delta ferrite. This is a single phase. Gamma, which we have here, it's called gamma or austenite. This is a single phase region also that we're having here. Here, and this is strep, which we have here, we also have a single phase region, and that region is the phase there is called the alpha ferrite. It's referred to as the ferrite phase. So these are basically the single phase regions. We have double phase regions here, like gamma plus liquid, the austenite plus the liquid here, and also here you have the liquid plus the cementite, see, this is a two-phase region as well. This is also a two-phase region. You have the gamma plus the cementite coexisting here. This is a two-phase region. You have the alpha plus the cementite region. This is a two-phase region, and this triangle here, this is an important triangle. It's called the intercritical area. You have the gamma phase and the alpha phase coexisting here. Here also we have two-phase regions. This is a single phase region, delta ferrite, which is this phase here. But in here we have two-phase region, and in here also we have two-phase region. This two-phase region the phases will be the delta plus the gamma here, and this is a two-phase region also, which consists of the delta plus the liquid. So this is a two-phase region as well. Now, so we acquainted ourselves. This is also a two-phase region, as I already mentioned. It's alpha plus the cementite, so that you have the ferrite plus the cementite coexisting together. There are three important points here on the phase diagram also. Let us look at them. This is, or before that, let me just tell you some transformation which is very clear in the phase diagram, easier to cover at the beginning. If I ask you what is the melting point temperature of let's say of iron, what is the melting point temperature of iron? You can just go on the phase diagram. That's 100% iron, 0% carbon. So you just go up. This is all solid phase that you are having here, that's the area of the liquid. So basically that will be, that will be the melting point temperature of the iron, 1538 degrees centigrade. So you can say that. Notice one other. Yes.
الحين اي اريا عندنا مثلا صايره نفس التراينجل تكون لازم فيها دبل فيز؟
لا ما قلت كذي انا. هذه الاريا سنجل فيز صح؟
بس مو شبه التراينجل.
يعني مو قضيه تراينجل ولا مو تراينجل. I am showing you the phase diagram and you have the single phases and double phases there. يعني if you want to say that this is not a triangle, this is a triangle, it's not a triangle. لا. You have a two-phase region here. صح؟ So it's not necessarily that it has to be a triangle. ما له علاقة بالgeometry. These are solubility lines. Okay?
تمام.
So let's notice this also. There is one thing that we have studied, I guess, in chapter 4. If you remember that what we said here, that no, not here, it is in chapter 4, I guess. Yeah, in chapter 4. If we heat up the iron will be from room temperature to these higher temperatures will have at 0% carbon will be in the form of the alpha ferrite, and the alpha ferrite has a BCC crystal structure, right? You remember that from chapter 3. So the alpha ferrite has a BCC crystal structure. As we increase the temperature, it stays as it is until we reach 912 degrees centigrade. It transforms to the gamma austenite, and the gamma austenite has an FCC crystal structure. What do we call that? The same material, iron, going from a BCC crystal structure, transforming at higher temperatures to the FCC crystal structure. What do we call that phenomenon in the material behavior? Polymorphism. Remember? Polymorphic. So iron is a polymorphic material. When you increase the temperature, actually, it changes its crystal structure from BCC crystal structure to FCC crystal structure. If you increase the temperature further and further and further, again it is going to transform to another crystal structure. In this case, we have the delta ferrite, and the delta ferrite is again a BCC crystal structure. So it goes again polymorphism. Polymorphic material changes to again a BCC crystal structure, and then afterwards it changes to the liquid. What is the crystal structure of the liquid? What is it, guys? What is the crystal structure of this now? Of this phase? I'm waiting for answers. How many people are we having here? This is a liquid, does not have a crystal structure, does it? I can fool you into this, huh? So don't get fooled by that. Don't get tricked. This is a liquid. So when it goes up there, this does not have a crystal structure. So crystal structures are for solids only. عشان جاوبت من ساعة مو تدش علي كل دقيقة وتسأل. أنا سألت ليش ما تجاوب؟
لا ما بتجاوب، عندي سؤال.
اسأل.
الحين شلون دكتور عرفت ان يعني اللي هو الالفا بي سي سي والجاما اف سي سي والدلتا بي سي سي؟
Because we know them. We know that the gamma is FCC, and you did not study that in chapter 3.
بلى دكتور بس
ما قلنا عن جاما اتس اف سي سي. ليش هناك ما سالتني السؤال وقلت لي شلون نعرف ان جاما اف سي سي وبيتا؟ because this is how they are. شلون اعرف ان انت عندك قلب في بطنك ومعده وما ادري شنو؟ we look at it لا through X-ray we can see you have a heart او نشرحك نشوف شنو داخل بطنك، صح؟ For us here درسنا دي في chapter 3. From the coordination number, we know normally people use the coordination number to know what type of crystal structure we are having in the material. Okay. So this is what we said. So we know that the iron is a polymorphic material. It changes its crystal structure as we change the temperature of the material. Now, also in this phase diagram, there are important points there. One of the important points is this point. What does this point look like? Something that we have studied in the previous systems, in the previous phase diagrams.
Eutectic isotherm point. Eutectic point.
Eutectic point, exactly. This is a eutectic point. Why? Because we are going from a liquid here to two solids. It's the same as what we did there. From the liquid to alpha plus beta. So this is basically the eutectic point. Now, how can we write the transformation equation for the eutectic point? We basically say we go from just above the eutectic point to just below the eutectic point. So how do we write that equation basically? We can say we have a liquid, صح? We don't need to memorize that. I can be asking you that. So you're going from liquid at a composition of how much? A composition of how much? It is mentioned here, 4.3% carbon, صح? 4.3% carbon, and that goes to, that's the equation, at 1147 degrees centigrade, and it goes to what? Just below the eutectic isotherm, we have two phases, the gamma plus the cementite. So the gamma will have a composition, of course, plus the cementite, Fe3C, and that also has a composition. What will be the composition of gamma? To find that, once we are below the eutectic isotherm, we can draw the toy line. We intersect the gamma here, because this is the gamma phase. So it basically has 2.14 14% by weight carbon. I forgot to write here percent by weight. Okay, and the cementite from that same toy line, it forms at 6.7% by weight carbon. I could just say the weight percentage in the cementite blindly without looking at it. Why? Because actually the cementite would not form except at 6.7. The cementite phase forms only, as I'm mentioning here, at 6.7. So you don't even need to read any number there. You just say 6.57 because it forms at 6.7. Now this is the equation, the eutectic transformation equation, which we are showing here, and it is happening at 1147 degrees centigrade. Another point which is important also is this point, and that point is very similar to the eutectic point, but here it happens at a much lower temperature and a different composition. And the transformation actually occurs from a solid to two solids here. Here it was from liquid to two solids. Here it occurs from solid, which is gamma. This is basically gamma. You go down from here, from a solid gamma to two solids, which is the alpha plus the cementite. So if we want to write the transformation equation for that also, we can do that, going just above and this point is called the eutectoid in this case. To differentiate between it and the eutectic point, we call it the eutectoid. So we go, if we want to write the equation for that, we say just above the eutectoid isotherm, and the eutectoid isotherm occurs at 727 degrees centigrade. So we can write that equation for this as well. So we say gamma at what composition? If you read down there, it is 0.76 basically. So you have 0.76 I'm not going to write the rest, okay? Percent by weight carbon. It's by weight carbon. That's the gamma, and it transforms at 727 degrees centigrade. See, I don't memorize these equations. It is just I'm reading everything from the phase diagram. To which phases? To the alpha plus the cementite. So it's alpha with a certain composition plus the cementite. 3C, and that also has a composition. If we want the composition of alpha plus the cementite, we just below the eutectoid isotherm, we draw a tie line, and it's going to intersect here for the alpha, because here we have the alpha. It intersects at 0.022, so that's the composition, 0.022% by weight carbon. And the cementite, I don't need even to read that. It forms only at 6.7% by weight carbon. Okay, I'm not going to continue that. That's the eutectoid transformation equation that can be represented in this one. We have also another important point, and that is that point. It's not very important actually for us. We have another point where the transformation also occurs, and this is called the peritectic. This is called the eutectic. This is called the eutectoid, and that is called the peritectic. And the peritectic, basically, the transformation occurs through that point there. It's a point which has similar behavior as the rest, and the transformation occurs from. You can go with the transformation this way or that way. Okay, so basically it goes from delta plus liquid to gamma, basically. So delta plus liquid to gamma. You can find using the Lever's rule and the tie line and get the composition of each one of these as well in the way that you want, in the same way that we did for the other ones. One important thing also on this phase diagram we need to notice here, as you can see here. Of course, this is the liquidus line, and this is the liquidus line. All the liquidus line. Above that line is everything is liquid basically. As you add the carbon content to the material, to the steel, basically, you can notice that it has that same behavior there. The melting point temperature decreases, and if you're basically at nearly 4.3%, that is the eutectic point where you have the minimum melting point temperature. But of course, with that high amount of carbon, you are having cast iron basically in that regions, and high carbon content is not required for the steels, and basically formability of the material gets influence, and that's why not much application is there, much less application for cast irons than the steels. Steels need to be at low carbon contents there. One other thing, notice that the austenite phase, I can say what's the maximum solubility of carbon in austenite? How much is the maximum solubility of carbon? That if we add carbon to the austenite, it does not transform to something else. Notice, if this is the austenite phase, this is the region of the austenite phase here, all that region, single austenite phase. Whatever carbon atom, or whatever carbon material we add, it can accommodate. It has high solubility basically, and the maximum solubility occurs at the eutectic temperature, which is 2.14% by weight carbon. So it has high solubility of carbon specifically at that temperature. For the ferrite phase, on the other hand, you can notice what the maximum solubility is. It's basically 0.022. That's the maximum solubility of carbon in the ferrite phase. it's much less than the solubility in the single austenite phase. The austenite phase is made of steel, of iron atoms, and the ferrite phase is made of the iron atoms only. The only difference between them is the crystal structure. This has an FCC crystal structure, and this has a BCC crystal structure. You see, the type of crystal structure actually changes the solubility of the material here. This maximum, so you see the difference between this number and that number, it's nearly 100% more carbon content it can accommodate. The austenite phase can accommodate much more carbon content than the ferrite phase. As you could see down here, it has much less carbon content that it can accommodate. The solubility of carbon in the ferrite is very little. Solubility of the carbon in the austenite phase, which has an FCC crystal structure, is much more. Why? Because, as I am implying, it's because of the crystal structure. One of the important points is the crystal structure. Of course, higher temperature also causes more solubility, but because of the crystal structure, this has an FCC crystal structure. The lattice parameter, if you remember, this is cubic, so it's A by A. The lattice parameter in the FCC crystal structure is bigger than the lattice parameter in the BCC crystal structure. So we are not talking about one dimension, since we are talking about volume here. So it's A times A times A. So it actually cubic of that dimension, basically, which makes the FCC crystal structure, making it much more soluble to the carbon content than compared to the BCC crystal structure. Lattice parameter in the FCC crystal structure is bigger than the lattice parameter in the BCC crystal structure, and this is the reason for why we are having that. So these are important things that we wanted to talk about. Now let's just read them out, what we already said. The phase diagram concept that we talked about, the compound. We said that the cementite is basically a compound, and it forms only at 6.7% by weight carbon, and we said that it has this fixed composition. We already talked about that. The iron carbon phase diagram shows three distinct points: the eutectic, the eutectoid, and the peritectic, and we looked at the transformation equation for each one of them. We also said on the phase diagram it extends up to 6.7% by weight carbon only, because we are not, first of all, interested in the graphite. Then the maximum point that we need actually, which will be 6.7, because the cementite forms at that composition. We also looked at the important points there. We said that the iron carbon phase diagram is one of the most important ones, and we also said the pure iron goes through this polymorphic transformation there, and we also talked about that, so we don't need to look at that again. Carbon, we said, is an interstitial impurity, as in when we dealt in chapter 3 with solid solutions. So it is interstitial solid solution which is forming. In any of these cases, we have interstitial solid solution. And we also explained why we have the solubility of the carbon in the gamma phase is much higher, 2.14, compared to the ferrite phase, due to the different crystal structure. In the alpha phase, it's BCC, and in the gamma phase, it is FCC. So this is what the above solubility is high. Beyond that solubility, actually beyond that solubility limit, the cementite phase basically forms. In this case as well, if you increase the amount of carbon there, the cementite phase is again forming there. Cementite is a very hard and brittle phase of steel, and makes the material much stronger. This is a classification of the steel, of the ferrous alloys, basically. Just a revision of what we have done before. Pure iron, we have basically less than 0.008% by weight carbon, not much used actually in pure sense. The steels are from 0.008 to 2.14 basically. We have it categorized as low carbon steels from 0.2, yani less than 0.25% carbon. And applications for these steels are in the car body panels, beams, sheets, in the tubes. We have the medium carbon steels from 0.2 to 0.6, and these are used in shafts, gears, bolts. And then we have high carbon steels, which is between 0.6 to 1.4 basically. Normally not above 1%, but formally we are saying 1.4, and these are used to make wires, springs, knives, chisels. These are, and then we have the cast irons. Cast irons are between 2.14 to 6.7. Normally does not go more than 4.5 in terms of composition, or 4. Which I'm mentioning here, 4.3. And these are used in making the machine body, cylinder blocks, the engines, yani, in these applications. Now I'm giving you this out of the blue. Why? Because I just needed to give you a slide which can give you applications for the different types of the steels here. More or less, I'm concerned the grouping we did before, but you have the applications, which material, which machine elements are used, from which material they are made. So this is an important slide for you when you do your design course. For example, the selection of the material for different machine elements, for example, you can refer to this page. Now I guess I'm going to stop because I don't want to prolong this more. Next lecture we are going to finish this chapter. I wanted to finish today, but it was not possible. Any question, guys?
دكتور.
Yes.
As we have more atomic packing factor, اللي هو شو اسمه.
Yes.
اي دكتور solubility تزيد يعني as we increase the solubility the atomic packing factor should be higher.
Let me, because